In this video, I first want to review our mini ALU project. I basically want to describe what we did in the project formally, but not for the sake of being formal. I mean, this is a math class and we know how to be formal. The actual reason is that you also saw in the exercises that a formal description can be in the form of something like system Verilog. And with that, you can describe hardware. And from that description, you actually can build actual hardware. So you can later go the way around from the formal description, which has a bad reputation because formal usually means not relevant for practical things. From this formal description, you can actually build something like a mini ALU in actual hardware, or you can go to a larger scale. What I will also show you, and what will be the topic of the next lectures, is the ULM lecture machine. Some computer which exists in form of a virtual machine, but also in form of hardware. And here I basically first give you a formal description of what you can do with the ULM. Basically I describe parts of its architecture and how you describe the instructions. In this video I will mainly focus on the ALU instructions, but then you get an idea how this formal description will look like. And then later in this lecture you basically do also the way around. You will use a tool called ULM generator, where you can specify with some formal description an instruction set, and from that you can generate either a virtual machine or actual hardware by generating with this tool from your formal description some system Verilog code, and from that you can realize your computer on a FPGA. Before I show you a few examples with the mini ALU, examples that we can do after the last exercise, some simple computations, stuff like that, let's do some kind of formal description first in advance. You see that I'm describing here basically the most essential parts of the mini ALU. We have 8-bit instructions. We have 4 registers. Each register has 4 bits and can be identified as register 0, register 1, register 2, register 3. And then we also have this status flags, which will be updated after an addition or after a subtraction. Let's go through a few examples. If I use the instruction with this bit pattern 1 0 1 1 1 1 0 0 and then press this button, you will see the effect is that afterwards in register 0 we have this bit pattern just once. And this will be displayed of course in hexadecimal, so you will see an F. And how was this possible? We were building hardware which was using from this instruction these 2 bits as the opcode. It was identifying the type of instruction, and we denoted it as op. And if the opcode is 1 0, these 4 bits, which we denoted as X, Y, were identifying what kind of data gets copied into a register. And into what register? The destination register was identified by these 2 bits. And we denoted this as set in this case. And that means we formally can describe the operation as follows. If the opcode is actually 1 0, then the effect will be the bit pattern XY gets copied into register set. So with this set, of course, we identify a register, and here it actually would be better to use here not decimal representations for the number, but write it down binary. So this would be actually register 0 0, this would be 0 1, this would be 1 0, this would be 1 1. Let's change this example a bit. Let's say this bit pattern in XY would be 0 0 0 1, and the destination register would be 0, 1. Then the effect should be that after pressing the button, you see here 0, 0, 0, 1. And in hexadecimal representation also 1. And with that, we can move some data, copy some data into registers. So for example, with this instruction, actually here I want to have a 0, we would copy a 2 into register 2. Okay, so kind of clear what this opcode specifies. Now let's go to another example where we have actually, now here I have to erase a few things. Maybe I erase it and come back. Next I want to do some computation. Let's say I want to add this bit pattern with this bit pattern and store it in here, in register 3. For that I can use the following instruction: 0, 0, 0, 1, 1, 0, 1, 1. Here we have the opcode 0, 0, so we use the same bit field for identifying the type of operation, but if the opcode is 0, 0, then the remaining bits were considered to be grouped differently. We have a different instruction format here. This group was denoted as X, this here as Y, and this here as Z. And the meaning of this instruction was the following: if the opcode is 0, 0, then a 4-bit addition gets carried out. We were using for this 4-bit addition this notation that we were using a plus circled. To this bit pattern stored in register X, we were adding the bit pattern stored in register Y, and we were storing the result in register Z. And then we also update the status flags. So the result of that operation should be that afterwards we have here the bit pattern 0, 0, 1, 1. We add 1 plus 2 and the result is 3, represented as binary. Then when we look at the status flags, we should not have a carry flag, because in unsigned interpretation we were adding 1 plus 2, the result 3 can be represented with 4 bits. The result, interpreted as a signed integer, is not negative, so the sign flag also would be 0. The most significant bit is 0. If we interpret this as signed integers, we also have 1 plus 2 and the result 3 is also correct. So the overflow bit is also not set. And of course the result is not a 0-bit pattern, so we also don't have a 0 flag set. Okay, and similar to that we also can do a subtraction. For example, subtract register Y from register 1. Then the meaning of this operation was that we do the following with opcode 0, 1. We have the same meaning, the same format for the instruction. We do the subtraction register X, the content of register X, minus a 4-bit subtraction, the content of register Y, and we store the result in register Z and update the status flags. So in the result only the 2 most significant bits in register 3 should change to 1, 1. And if we consider this as a unsigned integer computation, then we were computing 1 minus 2. The correct result is not representable, so we should get a unsigned integer overflow. The carry flag should be set afterwards to 1. In the result, the most significant bit is set to 1. So in signed interpretation it's a negative number, so the sign flag will be set to 1. And if we consider this as a signed integer computation, then we were computing 1 minus 2 and the result is -1, correct. So the overflow flag would not be set. So we leave it at 0. Now if we would, for example, like to compute register 2 minus register 1, then we just have to swap in the instruction the content of field X with the content of field Y. So we simply can make this here quickly in green. And then the result in register 3 should be afterwards 0, 0, 0, 1. And in this case, we don't have an unsigned over flag. So we can change the carry flag to 0. And the result has a 0 in the most significant bit. So the signed flag also should be 0. So we can change it here to 0 and here to 0. Okay, now let's look at that in Circuitverse. Okay, so let's redo this. First we want to load this bit pattern with just ones into register 0. So when I press the button, you will see here an hex F. Bam. Then let's load 0, 0, 0, 1 into register 1. When I press the button, afterwards you should see here a 1. And again, bam. Then the value 2 into register 2. Again, when I press the button, you will see here hex 2. Then we do the addition of register 1 with register 2 and store the result into register 3. So 1 plus 2 should give us here a hex 3. Bam. Then the subtraction. So here we compute register 1 minus register 2. So this should give us a hex F here. And then we swap here the operands X and Y. And then we should see in register 3 the 1, because we compute 2 minus 1. Now for a useful computer, we have to improve things a bit. We have to scale things up. For example, the size of the registers. On the ULM, these registers will be 64-bit registers, and with that you can do some actual useful computation. And we will have more than just 4 registers. The ULM will have in total 16 registers, not just 4. And we also need more than just 2 operations. I mean, we were using 8-bit instructions, and from these 8 bits we were using 2 for the opcode. So we can have at most 4 different kind of instructions. This is certainly not something where you can do useful things with just 4 instructions. Now, when we look at the ULM, you see the instructions are now 32-bit instructions, and you see that I'm using 4 boxes for describing the bit pattern of an instruction. That means in each box we have 8 bits, and 8 bits can be represented with 2 hex digits. That means if you see in a box a value like that, 1, 0, it's not a binary representation, it's a hexadecimal representation. In binary that would be 0, 0, 0, 1, followed by 4 zeros. We will use the box here, the 8 most significant bits for the opcode. And that means we have 2 exponent 8 or 256 different opcodes. So we can realize lots of different operations on this machine. You also see that we have now more registers, and each register has a larger size. So on the following slides I will just show you the first 4 registers, which will be sufficient for most examples. But also note that 16 registers can be represented with hex digits from 0 to hex F. So that means the name, the symbol used for representing a register is actually a bit pattern, which will be very useful again for describing the instructions. Then you also see that for each register, for each 64-bit register, I'm again using boxes where again each box represents 8 bits. So we have here 8 boxes, and in each box you can describe the bit pattern with 2 hex digits. So in total, the content of a 64-bit register can be represented with 16 hex digits. So in short, if you see a box, it represents 8 bits, with one exception, the status flags. The status flags are just bits, so there a box is just a bit. So again, these are just 4 of these 16 registers, and each box, except for the boxes here, represents 8 bits. Here every box represents just 1 bit. But let's begin with some instructions that just store some value in a register. Then the status flags do not matter. Here you see a very brief description of an instruction that you can use to copy data into a register, and the data that you want to copy into a register is part of the instruction. It's encoded in the instruction, and such kind of data is called an immediate value, because you don't have to first load this data somehow from memory into the instruction. And memory, by the way, is anyway a different topic. We are now talking just the ALU and care about the memory later. Now let me explain you by example the meaning of this description and how this instruction can be used, and why it is actually required to be a bit more formal about the description of these instructions. So in short, this description tells you that if you have an instruction with this opcode, this will be the effect of this instruction. What happens when you execute this instruction, and what happens depends on the remaining bits. Now let's go through this with an example. So an instruction with opcode hex 10. And this instruction will copy something into this register, into register 1. So with the next 4 bits, I can specify the destination register. So 4 bits will be used for specifying that. That means 1 hex digit. And let's say, like in the mini ALU example, I want to copy a bit pattern where all bits are equal to 1. Then in hex representation, that means I just have F, because we have here 20 bits, so it's a multiple of 4. So we have 20 bits all equal to 1. And then this 4 bits refer to D, and this 20 bits refer to the immediate value. And the effect will be that after this instruction was executed, you have this bit pattern being copied into this register 1. Now you see the problem. Register 1 has 64 bits. So what does it mean to copy 20 bits into 64 bits? And the meaning will be that these 20 bits were copied into the 20 least significant bits, so into here. And the remaining bits will be set to 0. This is called a 0 extension of the bit pattern. So this will be what you see after this instruction. This is the 0 extension, this is the bit pattern that you specified as part of the instruction. Now what has this to do with this strange description? Let's just plug in the things after the instruction was executed. Well, on the left hand side we have the unsigned value of a bit pattern in hex with 5 hex Fs. And on the right hand side we have the unsigned value of register 1. And in register 1 we have 0, lots of zeros, and then we have the bit pattern that we specified. And these two values equal to each other. And this is basically what this instruction tells you, that after it was carried out, the value here will equal the value here. And this is only possible if you 0 extend the bit pattern on the left with zeros. Otherwise you would have a different value. So actually quite simple. Now let's compare this with the next instruction. You see basically just two things have changed. We have a different opcode and also the description changed. It's somehow using this notation for describing that a bit pattern is considered to be a signed integer. Let's simply first think about the effect if I use the same instruction as before except for the opcode, which is actually meaning that I'm using a different instruction. But you know what I mean. I'm just changing here the opcode and the rest is as before. So again, this describes D. The instruction is using the same format as the previous instruction, and this refers to the immediate value. And here the effect will be that afterwards in register 1 I will have all bits equal to 1. And this is actually called a sign extension. What happened is that actually this is the data that was specified in the instruction and was copied into the register 1, and the remaining bits were just extended in such a way that the sign value of this here equals the sign value of the immediate value that you specified. Let's check that out. The sign value of this here, 20 bits, all equal to 1. That's a -1. The sign value of this 64-bit pattern, so we have here 16 Fs, is also -1. So it's the same. If we would have 0 extended it as before, the values would be different. The value then, the signed value of zeros, and then 20 bits all equal to 1, would actually be the same as the unsigned value of 20 bits all equal to 1, which by the way would be the size of 1 megabyte, 2 exponent 20 minus 1, so about 1 million. So in short, later we will say that this instruction with opcode 1, 0, the instruction before, will always 0 extend the immediate value, so that the unsigned value gets preserved when you extend it to 64 bits, whereas this instruction with opcode hex 11 is sign extending the immediate value to 64 bits. And for that I want to do another example with the very same instruction, where you see that sign extension sometimes fills up the bit pattern with 1s and sometimes also with 0s. So I will use the same instruction, that means the same opcode, but with different operands. The destination register again will be 1, so I still want to write something into here. So make that clear. This here refers to the destination register, to D. And the remaining bits now will be in hex 7, and then just all bits equal to 1. So hex Fs. And the result will be that this immediate value gets copied into register 1, into the 20 least significant bits, and the remaining bits will be extended such that the signed value stays the same. And for that we have in this case to 0 extend it. And I'll tell you in a second why. If you look at the bit pattern represented by hex 7, and here I want to be explicit, so I use this prefix 0x followed by the hex digit, then it's clear this is a hex representation. In binary, that's 0, 1, 1, 1. So that means the most significant bit is 0. And this is something that you should memorize, that in the hexadecimal representation, the values from 0 to 7 have a most significant bit equal to 0. So the sign would be non-negative. And from 8 to F, the most significant bit is 1. That means it's representing a negative value. So in short, if this immediate value has on the left a digit from 0 to 7, it's a non-negative value and it's getting 0 extended. If it's having a digit from 8 to F, it gets extended with 1s because it's a negative value. So this is another ALU instruction, but don't worry, I will not show you each and every ALU instruction, and also don't worry, you don't have to memorize all these opcodes, the corresponding instruction format, and all these descriptions. However, you should be able to understand the meaning of these descriptions, for example, expressions like here, and you also should be able to apply concrete instruction to a concrete case. So let's do this. Let's consider a concrete example. For that, I first want to have in register 1 a nice value, the value 1. So we have mostly zeros, except for the least significant bit, which will be 1. Okay, and then we also consider a concrete instruction with this opcode hex 1, 2. For example, the next hex digit would be 3, then hex 1, hex F, hex F, hex F, hex F. That means this 16 bits here are all equal to 1. Now, it's about to understand what would happen if we now would execute this instruction. And you will see it's not relevant what we have in all these boxes here. Basically, you can consider this bits here as undefined. First, you look into the instruction manual and check out the instruction format, and then you see that this here is denoted as Z in this instruction, this here is Y, and this here is the immediate value. Then we can look into this description, which tells us how actually addition gets stored into a destination register, in this case register Z, which is register 3. Now let me first show you that this description can be used actually to predict what the result in register 3 will be, but actually these formal descriptions are not supposed to be a recipe for how you actually do these computations. It's just a formal description of what you will see afterwards. But if we would follow this description, we would probably begin with this part, which tells us that we, for example, have to consider the bit pattern stored in register 1 as an unsigned integer. So the unsigned integer would be 1, which is simple. The unsigned value of the immediate value is also kind of simple to determine if you know that if you have 16 bits all equal to 1, the value is 2 exponent 16 minus 1. Because if you would add a 1 to that, you would get a bit pattern with in total 17 bits. The most significant bit would be 1 and all the other bits would be 0. So 2 exponent 16. And that's how you could possibly come up with this. So these two unsigned values then would be added. So that would give us 2 exponent 16. And then we have this part here. Then we apply this mod 2 exponent 64, which means that we divide this here by 2 exponent 64 and take the remainder. And the remainder would be 2 exponent 16. So basically 2 exponent 16 is this here. And this value now gets stored in register 3, represented in hexadecimal or in binary. So that means if I write it down here, then it's of course represented in hexadecimal. Then the result that we would see is 0, 1, followed by 4 zeros. And here we all have leading zeros. Now this method following this description here and carrying out the instruction manually works maybe in this case, but in general it's not the easiest way. Let me show you how I would do this. I would take this value or this bit pattern, write it down for example here. Now this value is supposed to be an unsigned value and it's supposed to be added to another unsigned value represented with 64 bits. So I first extend it to 64 bits in hexadecimal. This means I extend it with hex digits so that in total I have here 16 hex digits. Then this is representing 64 bits. And below that I will write this bit pattern in hexadecimal. So 0, 0, 0. Here also zeros, and here we have a 1. And then I simply add it, like I learned it in school. It's just in hexadecimal, not in decimal. So we begin with this part, hex F plus hex 1 would be hex 0 carry 1. Then we continue with this part, which gives us hex 0 carry 1, and so on. And then we have here a 1, and the remaining hex digits all would be 0. And with that, I get the 64-bit pattern in hexadecimal. Now in general, you will have here a 65th bit, of course, which in this case would be 0. So basically from that, you also see the carry flag, because we know the meaning of things. So that means in this case we, from this computation already can see the carry flag would be 0. We also see that this bit pattern is not a 0-bit pattern. That means the 0 flag would not be set. We also see from this part here that this leading digits are not 8 or more. Again, the digits from 0 to 7 have a most significant bit equal to 0. So that means we have non-negative plus non-negative, and the result is also non-negative. And from that we know that we don't have a sign overflow. And we also see from this that we don't have a sign flag. So we basically can do this very simple. So again, these formal descriptions are not supposed to be a recipe for doing these computations. They are just characterizing these computations. But of course it's helpful if you know the meaning of certain things. For example, the meaning of this mod 2 exponent 64 is that the result, which is in general a 65-bit result, gets truncated to the 64 least significant bits. And if you know the meaning of certain things, then you also know how to apply them for actual examples. Let me also show you the formal descriptions for updating the status flags. That's here. It's, for example, here characterizing in which cases the 0 flag is after a instruction set to 0 or to 1. It's characterizing it, but it's not describing how the architecture or how you should determine this 0 flag. But the meaning of it is that you first carry out formally this addition of unsigned integers, and the result in general will require 65 bits. This describes that from this 65 bits you just consider the 64 least significant bits. You truncate it to 64 bits. And then you check whether what is left would be in unsigned interpretation a 0. And that's it. So with descriptions of instructions for the ALU, you can basically understand all the ALU instructions. And in the same way, we can describe fetch instructions for moving or copying data from memory into registers, or store instructions, which is doing the things way around, copying data from a register into memory. And in a similar way, we can describe I/O instructions, which are basically also just fetch or store instructions. And we also can describe how a program which is in memory gets sequentially executed. So this will also involve the jump instructions. And then you will get in the exercises a piece of paper like this here, where you see actually ULM lecture machine on paper. And that's how we call this exercise, ULM on paper. Here you see from the ULM some part of the memory, some memory cells. You see here some part of the CPU, for example here, some part of the ALU and the register files. And then you will learn in the exercise how to actually run this program, which is already loaded into memory instruction by instruction, so that you understand the meaning of the sequential execution, that this 4 bytes, for example, represent an instruction which will be executed first, and then this instruction will be executed a second instruction, and some of these instructions are actually jump instruction. So what you already saw in the top-down approach in this lecture, where we described things on a higher level, now will become more clear, because we now can precisely describe how data gets moved around in the computer, how it gets decoded, and so on. So that's it for this video. See you in the exercises.